Uh, uh, Good morning. Welcome back to school. Spent a week doing, I don't know, other things, and now we're gonna be back in assignment land. All right, are you ready, people? It's April 20th when I'm recording this. I don't know when it is when you're watching this. Depends on which class you're in and all that kind of stuff. Today we're going to be using natural logarithms. I mean, it's good to be natural, right? Natural remedies for things like zinc and quinine. That'll do it. Kill coronavirus. Um, right. As we've talked about before with logarithms, I'm sorry about the shine of the lights. I can't do anything about that. We got logarithms are can be done to any base. We've even changed the base if we wanted to. But you do have two special buttons on your calculator for two particular bases of logarithms that we use all the time. We got the log button, which is log base 10, and we got the ln button, which is the natural logarithm base e. You might be wondering why e doesn't seem like it's very useful. Like it takes you like all kinds of weird rules in order to even define the thing, like what is e and discovering what e is. But in terms of functions and whatnot, e is one of the most used functions, like exponential functions with base e, that there is for any kind of other thing. In fact, I was just thinking about a list of things that powers of e get used for, um, and well, we obviously have in our book we've already done compounding interest. It's a good way of modeling things that do with money and investments. We also use natural logarithms to describe population growth, which is big, or the growth of anything. It could be population, or it could be virus production, things like that, or bacterial replication. It could be on a logarithmic scale. But yeah, lots of actual things in the natural world. I know that we use base E stuff when we do Newton's law of cooling, which is it's a really basic deal here, but it would tell me how quickly the temperature is going to go down in my cup of coffee here, or tea, or water, or whatever. It looks at the difference between the air in the room and how warm your fluid is, and then you just trace it on a logarithmic scale that is e to the power of, and you can predict what the temperature will be after X number of minutes if you just let the thing sit there. You can change the temperature, and so the closer that your cup of coffee comes to like the normal air temperature, the rate of change slows down. So you get this gradual logarithmic curve. We do it in physics. We do natural log type problem with Newton's law of cooling's whole lab devoted to it. There's, in fact, a whole family of formulas that all follow this same type of strategy of using natural logarithms. Okay, so James has probably taken a whole course on these families of formulas, and it's hang on, I'm gonna remember what they're called. I remember. They're called differential equations. Anyway, so you take the derivative of one equation, you get a new equation, and then you take the derivative of that, you get another equation, and all of them are related, and they help explain like one phenomenon, like we've got acceleration, and velocity, and position, all that stuff. They're all a family of equations. So they are going to mention that one bit of that in the book. Also, last interesting thing, and this has to do with if you keep going on with math, if you end up getting to calculus, um, the formula y equals e to the x is probably one of the most interesting logarithmic equations in calculus. It's one of the most useful ones, and one of the reasons for that is if you take that curve e to the x, y equals e to the x, and in calculus, what we often want to know is what is the slope of a line at any particular point. This one if you go out to, let's say you go out to 2, the slope of the line there is e to the 2. If you go out to, let's say you go out to 3, the slope of the line at 3 is e to the 3. It is like it's called its own derivative. So it's so much used in calculus that anytime they use a logarithm in calculus, they're using a natural logarithm. In fact, they don't even say natural logarithm. They just say logarithm, and you know to say ln rather than log base 10. Okay, so we know that on our calculators, this setup works. If you log base 10 of a number, big number, you want to write it in a different way. You want to find its logarithm, you want to find its exponent. You have this as being an equivalent statement in exponential 10 to the logarithm equals that number. And same thing is true if we were to do log base e, or the natural logarithm of some number. It follows the exact same rules because the only thing that's different here is the base. Okay, the base is not 10 like in our base 10 system. The base is e, about 2.71828182828499049 or something like that. You're going to read a little bit about it this week, so just hang on. And so because it's a logarithm, it's just a different base of logarithm. It follows all the same rules as a logarithm would. It'll follow the inverse properties. It'll follow some of the identity properties. It'll have the product, quotient, power property. They're all in this as well. Natural logarithms follow the same rules as other bases. So I'm just going to quickly, I'm going to pause. I'm going to put them up on the board. You copy them down. You copy them from the book. But we'll just kind of review the properties of logarithms. It's been maybe a little while since we thought about that. Okay, first is the inverse property, which we dealt with to any base, but specifically today to the base e. E to the natural log of x equals x. It can be shown pretty easily if you take the inverse of it or you change the form of it, that is true. Also true is ln e to the x equals x. Part of the reason for that is that ln e, the natural log of e is 1. It's got a base of e to the e. So e to the what equals e? 1. So if all this is 1, then that x is all that there is. Anything to the 0 power is 1, so e to the 0 power is 1. We also have got the product property. The natural log of something that can be split up into factors equals the natural log of each factor added together. So ln a times plus ln b. And you can break that up into as many factors as you want to and break it down and add those answers all up. Quotient. The natural log of some number divided by another number is the natural log of the top number minus the natural log of the bottom number. And this is my favorite, power rule. If some number here can be written as to a power, you just pull that power out to the front and take the natural log of just the number all by itself. One of the most handy dandy ones that we've got. All these rules we'll have them, and then we'll show you a problem and say which rule do we need to use to pull this thing all apart, to deal with all the little parts separately. All these take more complicated problems and turn them into simpler problems. And in fact, I got this gift from Jeff White, and I could do those problems on this. This is a slide rule. This is like a calculator. This is a calculator up to about 1970 or so, and then people started, paying the big bucks for that Casio that could do some of the math. I have on here a way to do logarithms. I can do adding and subtracting of logarithms. You just have to go and look up the values of there. I'm not sure if this one does natural logarithms. I haven't read the whole instruction manual, but I could turn a simple, complicated multiplication problem or division problem or a problem with powers in it into addition or basic multiplication or subtraction. Last thing in terms of the theory behind all this, and that's going to be inverse functions. So what I'm going to do is first I'm going to take the function y equals e to the x, that special function in calculus that is its own derivative. And we're going to play the inverse game with it. We want to find out another equation that is like this equation, but is its inverse, right? It's like undone. It's the backwards version of the same thing. And so you can start off by putting this equation into, focus, this into your calculator. A nice, where's that E button? It's over there on the left, right above natural log. E to the x. And maybe that special line, y equals x. And have that graphed on your graphing calculator. It's exponential curve. And then you get your y equals x. So let me do this various colors here. Blue. E to the x. Here we go. It comes along and then it hits 1 and it climbs, right? There it is. E to the x. All right, we're going to discover what its inverse is. I'm trying to get this to focus, huh? Oh, there we go. It's better. Okay, so we switch the x and the y. Where'd that pen go? All right, I'm going to go after this equation right here. I'm going to solve for y. So I'm going to use the power rule. I'm going to take the natural logarithm of both sides. So it means ln x will equal ln e to the y. Got both of these rules here, the power rule, and I've got this rule right here, which says that ln e to the whatever equals the whatever. So I got ln x equals, or I can use the power rule. I can say y times ln of e. Ln of e is 1. So this side is just y, and I've got ln x. That is the inverse of this right here. So if you take a calculator, and you already got that first equation in there, and you put this second one in, where is it? Natural log x. You graph them on the same set of axes. You get that. And so the black one is the one that just happened. I'm going to do that one up here on the board in red. ln x equals y goes like this. Crosses at 1, that one crossed at 1, this one crosses at 1, 0, that one crossed at 0, 1. Okay, you can tell by the picture that they're inverses of each other. So again, this is y equals e to the x, and this one is, I should do it the same way, y equals the natural log of x. Okay, inverse equations of each other. There you go. That's kind of the theory behind these things. Now let's do some examples, and pretty much all I want you to think through is which one of these rules would we apply to pull this thing apart, or maybe we want to put it all back together and make it a simpler problem. Oftentimes we'll find that there's stuff in that problem that we can solve if we just either put it together or pull it apart. And stuff that we can start putting numbers to answers. Okay, so here's the first one. What can we do with that, right? Natural log of 6 times e. Well, 6 times e is a product, is it not? And the product rule here says we've got 2 factors. We can split those factors apart, right? Our 6 times e, well, it's hard, but I can do the natural log of 6 plus the natural log of e. And we already know what the natural log of e is. That's another one of our little rules here. The natural log of e equals 1. So this is natural log of 6, which you can either do on your calculator or you would look up in a table, plus 1. I can solve part of this without even using a calculator. Okay, so that was the product rule, and we're using this definition, this definitional type of rule. It's like an identity sort of thing. Okay, here's another one. Let me get rid of this one. That at least the work. So we did that. Okay, the next one is the natural log of 3e over x. right away you notice that, well, I did something a little bit different there because I put it over x, so we're definitely going to use the quotient rule. But on the top, it's very similar to the first problem. It's 3 times e, so there's the product rule and the quotient rule involved. So how would we pull that apart into more pieces that maybe we can solve for parts of it? Well, let's do the top part first. We would have the natural log of 3 plus the natural log of e. And then anytime we've got the quotient part, like that b there, it becomes minus the natural log. So it'd have minus the natural log of x. And as we had in the first problem, natural log of e is just 1. So maybe we want to do this. 1 plus the natural log of 3 minus the natural log of x. That's as spread out and solved without a calculator as we could. We could do this with a calculator, and then we're only left with one variable. So we simplified it quite a bit. We got a whole bunch of things we can put numbers to or approximations to. And we're only left with just tell me that one last thing. So we used the product and the quotient rules there. Okay, that one's done. All right, now we're going to do one that's got more stuff. Natural log of e to the 5x squared. Natural log of e to the 5x squared. Most obvious thing here is the power rule and natural log of e. So as soon as I see a power, I go right away, I'm like, that can go down into the front. So start solving that. I'm going to take the power and I'm going to put it out here in front of the problem. And that's what I'm left with, is basically natural log of e to the 1, which says is 1. So this part turns into 1, and I've got 5x squared times 1, or 5x squared is the answer to that, because the base of the logarithm and the base of this number, they match. So kind of like cancel each other out and do each other. Okay, so there's that one. That one looked kind of scary, but it really wasn't. And then our last one, I'm going to throw everything at it that I can. Natural log of 2x cubed over e to the 4th squared. How about that? Put that in your, I was going to say pipe and smoke it, but that's not appropriate for children. Put that in your disc player and listen to it, which doesn't really make sense these days anyway. Okay, what do I got going on here? Which rules apply? Well, there's a quotient, isn't there? There's something over something. Those somethings have powers on them. The whole thing has a power on it. And you've got products, 2 times x cubed. So let's do this power rule first. Okay? Pull that 2 out into the front. 2 natural log of this product quotient deal. And then let's pull the product apart. So we got, I'm going to go up here now, 2 natural log of, well, we got the natural log of 2x cubed. Yes, I could do that. Minus, let's do that, 2 times natural log of 2x cubed minus the natural log of e to the 4th. Okay, so I've got all that. Okay, next step is, this is actually a product still. So I've got 2 times the natural log of 2 plus the natural log of x cubed. And then over here we've got minus. And then this is the power rule. I can go 4 in the front, natural log of e, simplify that one more step. Okay, but wait, there's more. 2 times the natural log of 2, which my calculator can handle pretty well. And then I got the power rule here. So that'd be plus a 3 ln x. And then lastly, ln of e equals 1. So this is just minus 4 times 1, or minus 4. Lastly, that 2 needs to get distributed. And so I could leave it like this, Or I could go one more step, and I can have 2 times the natural log of 2, which my calculator can handle pretty easily, plus 2 times 3 is 6 natural log of x, and then we got minus 2 times 4 is 8. So you can leave it like that. Calculator can do that. Calculator can do that. You'd be left with this business here, as long as you tell me what x is, and I can finish this one off. That's about as spread out and solved as we can get. And so we stop there and we say, without the calculator, I can do all of that stuff using the power rule, the quotient rule, and the product rule, and this definition rule, this identity rule there too. All right, let me clear the board. You're going to have to do some of that pulling apart, but you might have to put some back together as well. Let me finish off with a couple of practical applications. Okay, friends. It has been in our book for a while. Continuously compounding interest is our very common friend as far as natural logarithms go. A for amount, like in the bank, as a function of P for principal. This is the amount I invested, times e to the rate, interest rate, times time. Okay, we've done that before. That is part of the family of natural base functions, which all kind of have the same setup. You can kind of relate what's in here to that right there. In general, n of t, t standing for time, equals n sub o, or n sub 0, I should say, being the original amount, where, times e to the k times t, if you want some exponential growth. Okay, exponential growth, k is bigger than 0. Growth. So you're talking about population, you're talking about interest, things like that that grow and get bigger. Or you can have the same exact thing except a negative in there. You know, see that k is less than 0. This would be decay, which would be like radioactive decay. This is like the cooling equation for my coffee mug. Okay, Newton's law of cooling. It fits this type of equation. All right, where the first thing is when we plug in a 0, and that value goes right there in front. So pause me and write all that down. So we'll work through one example problem that would be similar to what we would do in a physics class if we're talking about nuclear medicine. We're talking about samples of stuff and its decay rate. So there you go. Hit pause, and I'll sweep this away in like 3 seconds. 1, 2, 3. Okay, nuclear medicine, which might include X-ray technicians. It's going to include chemotherapy. It's going to include nuclear physicists at nuclear power plant that are developing things for medicines and for other applications and for making purifying chemicals and a whole bunch of things. You can watch periodic videos. Excuse me, I got all kinds of bodily functions going on this morning about that. So the problem here is I've got a 200-gram sample of chromium-49, which is probably one of the decay products of some type of nuclear fission. It would go on in Tennessee or something like that at one of the nuclear facilities there. And we want to know how long it's going to take for that sample as it's decaying, as it's shooting off particles and whatnot, heating up water, whatever, of this chromium-49 to get down to that there's only 5 grams of this stuff anymore. And the rule here is that its half-life, which is given the symbol lambda, it's the Greek letter L, that its half-life is 42.3 minutes. That means after 42.3 minutes, you're only going to have half of your sample left. So I'm just going to get an estimate here for starters. And if I start off having gone through no half-life, so I got 200 grams. If I go through one half-life, I'm going to have 100 grams, and then half of that's 50, and half of that's 25. And I keep going down, and somewhere between 5 and 6 half-lives, So 5 or 6, 42.3 minutes amount of time, I'm gonna have my 5 grams left. Okay, so we're gonna work our way through this, and first we're gonna start in kind of a general way because we need to find out what that rate is. Our equation was n of t equals NO times e to the kt. Now this is decay, so we're going to use the negative version. Negative k. T, that's our starting place. We're going to work with this equation here to get to our solution. So we're looking for when there's only half of something left. We have to figure out that rate first. We have to figure out what k is first before we can plug in our actual numbers. So this is always the way that you start these half-life equation types of things. We say we start off with 100%, we're going to end up with half. And then we go times e to the negative k, and then we're going to enter in the half-life, 42.3. So maybe we could treat t as like lambda here, but that's the first thing that we need to discover. So we need to discover what that value for k is. We know everything else. We know this is an actual number. Thank you, Dutch, for pointing that out to me this morning. And that's our only unknown. So we start doing the math. I don't really need that one there. It's just kind of hanging out. I'm going to use the power rule to pull this down into the front. That would be, I'm going to take the natural log of both sides. I'm going to take the natural log of e to the negative k times 42.3. That's going to give me, whatever the natural log of 1/2 is, equals negative k times 42.3 times the natural log of e. Natural log of e is 1. So now this is all I'm working with here. I want to solve for k. If I divide both sides by negative 42.3, there's my problem right there. That will equal k. Okay, at this point, I need my calculator. I can take the natural log of 1, which is 0, and I can take the natural minus the natural log of 2. Let's just do this fraction bar. Natural log of 0.5 divided by negative 42.3, and I'm going to get this decimal, okay? And get this decay rate. And I get that k is approximately 0.016386. And really, the more decimal places I use, the better my answer is going to get, but that is probably plenty. That is my value for k that I'm going to use in this equation up here. So now, the actual problem. I start off with 200 grams. I want to know how long it's going to take for me to get down to 5 grams. Okay, n of t is 5. I just don't know what t is. I know how much I started with, and there's e, and I got the negative, and here's my decay rate. Point. Oh no, I don't need the negative anymore, do I? Do I? No, I just need that value. I found out what k is. 0.016386. It's going down. There's going to be less of it every time. Times t. Now I need to solve for t. Okay, easiest way to start this off is to divide both sides by 200. That'll get the ball rolling. 5 over 200 equals e to the 0.016386, etc. times t. I'm going to take the natural log of both sides. ln of whatever that is equals ln of e to the 0.016386 t. I'm going to use the power rule to bring all that junk down to the front. 0.016386 t times ln e. ln e is 1. And then all I got to do at this point then is divide both sides by 0.016386, and I have t. So t is approximately whatever the natural logarithm of that fraction is, divided by 0.01636. Calculator time. I could have simplified that anywhere in there, but I decided just to leave it. Natural log of 5 over 200 over 0.0163866, enter, and it gives me a negative number, which made sense because I'm like, well, I guess I should have left that negative in there. Negative, 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 negative. Okay, so I get approximately 225 minutes. Well, let me divide that by that 42.3. It should be somewhere between 5 and 6, right? Negative 5.32. So I went through 5.32 half-lives in order to get down to exactly 5 grams in there. Okay, so 225 minutes would do the job. 225 minutes or 5.32 half-lives. Half-lives? Whatever. There we go. It's a little bit of a long process. It looks slow and tedious when I do it because I'm doing every single step. But the more you get used to using like the power rule to bring everything down, you can skip some stuff. You can say, well, I'm going to bring it down, I'm going to divide it over there, and that part's going to equal 1, so let me just take the natural log of this side divided by that number up there, and got my answer. Okay, so first you got to figure out what k is, and then you're going to go back to the beginning and plug k in, work your way to solve for t. Okay, so that problem there, half-life of a decaying radioactive material. I'll be available for math chats. I'm going to send you some stuff here. You're going to be doing a little bit of reading about natural logarithms, and you'll have reteaching to do to kind of practice some of the basics of pulling them apart, putting them back together. But they're just logarithms, just to the base of e, which is going to be, if you keep doing math, one of your favorite numbers to use. So there you go. I'm sorry that's a little long, but the copy hasn't kicked in yet. I'd rather talk slowly and clearly than just whip through all this stuff. Again, I'm available for questions maybe on Tuesday if you're the first period class. I don't know what it's going to be yet for the second period class, but no doubt I'm available to you. I love to talk about math, so let's do it.